In this example, I'm going to show you how to take the beam with 2-point loads and a UDL, the reaction forces previously worked out, to be able to draw the shear force diagram, and then to use the shear force diagram to be able to plot our bend moment diagram. This beam is subjected to 2-point loads and 1 UDL. Previously we had worked out the reaction forces, and the reaction force at point B was 9 kilonewtons, and the reaction force at point E was a value of 19 kilonewtons. Now to draw the first of the two diagrams, the shear force diagram, we're going to draw in some construction lines. So it will show us where the beam starts and ends, and where the supports are. So we'll draw these construction lines in. I'm going to draw in a 0 line. And we'll label this our shear force diagram. The units will be in kilonewtons, and we can label the horizontal line as being 0. Now to do the shear force diagram, what I'm going to do is I'm going to take the beam and reveal the forces on the beam and plot the resultant force that I have on the shear force diagram. So here I've covered up the beam, and as we uncover the beam, we're going to plot the resultant force on the shear force diagram. So starting off at 0, having moved the cover across, we see the first force we actually have is a force of 2 kilonewtons pointing downwards. So therefore I'm going to plot that as -2. The force going downwards will cause a vertical drop down to -2. As we reveal the beam, the resultant force stays the same, and hence our shear force diagram stays at a value of -2 until we reveal the first of the two support reactions. The first support reaction is a value of 9 kilonewtons, and that will cause a jump upwards, because the R is going upwards, a jump upwards of 9. So we're currently at a value of -2, and add 9 to that, and that will give us a value of 7. We can plot in our vertical jump up of 9. Then I'm next going to consider where we're at on the beam at the end of the UDL, but just before we come to the second support of 19 kilonewtons. So currently at a value of 7, we have 3 meters of 6 kilonewtons per meter, and that will give us a total weight of 18 from the UDL. So currently the resultant force we actually then have is, currently taken from 7, we're going to drop a further 18, the total weight of that UDL, and that will give us down to a value of -11. Over that region, we should have a diagonal line that we can plot in. Next part, we're going to move past the support to reveal the reaction of 19 kilonewtons. 19 kilonewtons is pointing upwards. That will cause us a jump upwards of 19 from a current value of -11, and that will take us to a value of, so -11 plus 19 gives us a value of +8. Then moving along the last part of the beam, the resultant force we have stays at 8 until we come to the very end of the beam to reveal the 8 kilonewtons on the very end, and that will cause us to drop from a value of 8 back down to 0 to close off our shear force diagram. And that's our shear force diagram drawn for our beam. To draw our bend moment diagram, what we need to do with the shear force diagram is to be able to work out the value for each of the areas we have enclosed on the shear force diagram. So each of these areas we need to work out the value, because we're going to use the area value to help us to plot our bend moment diagram. So in this case we have 4 areas, rectangles and triangles. So we need to work out each of these areas. Starting with the easy ones first. So the green area we actually have, so call that area 1. It's simply going to be the length by the breadth. We have a value of -2. The distance across, as we have in the diagram above, is 1 meter. So the total area we have is -2. Similarly, for the purple area at the end, call that area 4. Again, will be just length by breadth. It will be a value of 8 tall and 1 meter wide. That would give us a value of 8. Now to work out the area for the orange and blue areas, both of these are triangles in shape. So for the orange area, it's going to be the half the base times the height. However, we know the height, which is a height of 7, but we don't know the distance along for the base. To get that distance along for the base, we take our starting point, which is a value of 7, and we divide it by the rate of the UDL, 6 kilonewtons per meter, and that will give us the horizontal distance along. So this distance is 7 divided by 6, which is 1.167 meters. Conversely, on the other side for the blue triangle, the total distance across from B to E is 3 meters. So 3 meters minus 1.167 gives us 1.833 meters. With this information, we can work out the area for the orange triangle and the area for the blue triangle. Area 2 then becomes a half times the base, which is 1.167. Multiply that by the height, which is 7, and that gives us a value of 4.08. So this area has a value of 4.08. It's positive. Likewise, for the blue area, area 3, it's also going to be a half the base times the height, which is going to be a half times 1.833 times minus 11 for the height. And if you work that out, that gives us a value of negative 10.08. We're now going to use these values for the areas to help us to plot our bend moment diagram. To help us plot our bend moment diagram, I'm going to move our shear force diagram up. I'm going to draw in some construction lines for the start, the end of the beam, and where the supports are. and also where the crossover point is on the shear force diagram. And I'm going to draw in a 0 line as well. This will be our bend and moment diagram, and the units are going to be in kilonewton meters. Horizontal line is where we have 0 bend and moment. So we're going to use the areas we have on a shear force diagram to help us to plot points on our bend and moment diagram. To do this, we essentially add up the area we have on this shear force diagram. So I've covered up the shear force diagram. So the total area at the very start gives us a value of 0. As we reveal the shear force diagram at this location, at the first support, the total area we have is a value of -2, and I can plot that in. Move across. The total area we have shown on the shear force diagram is -2 plus 2, or 4.08. That gives us a total of positive 2.08. As we move across, we're going to reveal the next area. So the total area we have shown on the shear force diagram is the 3 areas added together, the -2, 4.08 and a -10.08. The resultant of that, when you add those 3 areas together, gives us a value at this location of a value of -8. Then by the time we come to the very end of the beam, we add together our 4 areas, -2, 4.08, -10.08, and a +8, and that gives us back a value of 0. The areas gives us the points on our bend and moment diagram, or the total of the areas gives us the points on our bend and moment diagram. Now we've got to join the dots to complete our bend and moment diagram. Starting with the easy parts first, we look at the shear force value, and that tells us the gradient on our bend and moment diagram. So to do the easy part first, in the first region we have a constant shear force of -2, and that's going to tell us in the first region we have a constant gradient of -2. So the gradient here is a value of -2. It matches the shear force value over that region. Likewise, looking at the very last part, we have a shear force value of +8. So that tells us in the last meter of the beam we have a line of constant gradient, and that constant gradient is a value of +8. Now, in the middle part of the beam, we need to consider the shear force value at the start, at the crossover point, and at the end. So looking at the shear force value at the start, it's a value of +7. So the tangent to the curve at that point will have a gradient of +7. Looking at the crossover point, where the shear force diagram crosses through the horizontal axis, the shear force value at that location will have zero gradient, therefore will be a flat line, and we'll draw a little tangent to the curve, horizontal line at that point. And looking at the end of the region where we have the UDL, we got a shear force value of -11. So we can draw a little tangent to the curve at the very end with a slope of -11. Now what we're going to do is to draw a curve in that matches the tangents that I've drawn in on red. So it's going to start positive. The gradient will get less to so to draw the bend moment diagram for the region over the UDL, we're going to draw in a curve that match the tangents that I've drawn in red. So initially starting with a positive gradient, as we move along the curve will maximum out at the crossover point, and then after that we'll continue on downwards to match then the final tangent as we kind of finish the region where the UDL is. Our bend moment diagram is now complete. Then points to note from our bend moment diagram: the maximum bend moment is not always the maximum positive value, but the maximum absolute value. The maximum value we have is a value of -8 kilonewton meters, and that occurs at point E. And then as well, points of contraflexure we can indicate on our bending moment diagram. It's where the bend moment diagram crosses through the horizontal axis. So in this case we have 2 points of contraflexure, and we indicate those as one occurs here, the second one occurs here.